go. And so what we have here is a triangle ABC. I've just said in the figure. So in the figure, we have been told that ED is parallel to BC and EC is parallel to FD. Okay, so remember, one of the things that we look out for in geometry are those parallel lines. So ED to BC are these pink parallel lines that I'm highlighting here. Now, the reason I'm making a point of highlighting them for us is because what we need to remember is that if we're going to apply our proportion theorem, we have to be working with a line that is parallel to a side of my triangle. So I have to make sure that these parallel lines coincide with the side of a triangle. And then ECFD, so these are these sort of slanted parallel lines here. So again, knowing where your parallel lines are very, very important, because we can only apply prop theorem in a triangle, essentially. We can't just work with random parallel lines. So those are the parallel lines we have. We are also told, and this is now where things get a bit new and a bit interesting, we are also given the following information. AD over DC is equal to 5 over 4, and then we're given some lengths. So we are told that AF is equal to 3x minus 5, you don't really have to put in brackets, and FE is equal to 2x units. So we've been given the length of AF and FE, not in terms of like it's 20 centimeters in terms of x, but we know the length. All right, so before we even get to the question, I just want to quickly jump back to this ratio that we were given here. What happened? This AD over DC situation. Now remember, and we said this right in our very first lesson on proportion and similarity, a fraction is the same thing as a ratio. Ratios and fractions tell us represent the same information, we just write it in a different format. So this could actually be written as a ratio of AD to DC is equal to 5:4. So whenever you're given a fraction, don't freak out about it. It's just giving you a ratio. And what you need to remember is that ratios and fractions tell us the same information. It's just a different format of how we're writing stuff. All right, so if we go back to the other information we had, I'm just going to write down what I know. So we were told that AF is equal to 3x minus 5, and FE, so this little segment here, is equal to 2x. Calculate the length of EB. Now, guys, there are lots of different ways that you can think about this. There are lots of different ways you can approach these types of questions. You have to find what works for you. But I find what works best for me is set up the ratio containing the thing that you want. So in this case, we want EB. Let's set up a ratio containing EB so that we can figure out what information we might still need in order to get there. Now, once again, there's lots of different ways you can set up this ratio. So we just need to be mindful of what we're working with. So if we go and highlight for ourselves that side length that we want, so remember, we are looking for EB. And EB is this yellow side down the left here. EB is a line segment in the greater triangle ABC. So I'm going to set up a ratio using that information. Remember, I've also been given this ratio that AD to DC is 5:4. So AD is 5 parts. Okay. So AD is 5 parts. You can use a variable if you want. And DC is 4 parts. Now, if you have a look at EB, that corresponds directly with DC. So that's great. I'm already starting to get a bunch of information that's going to work for me. So remember I said to you before, always start in your numerator with what it is you're looking for. So we're looking for EB. We then want to set a ratio up in terms of what we have. So we've got EB. And if we look at the top segment of our triangle ABC, we have that in relation to AE. So AB over AE, I don't know why I said AB, EB over AE would be equal to, now match it up. EB, I've just said matches up with DC. And AE matches up with, at the top, AD. And this is all because of our prop theorem. So remember, you have to give your reason. And if we're going to use prop theorem, we have to say the parallel lines, ED parallel to BC. If you're not going to use prop theorem, guys, remember you can use line parallel to one side of triangle. That's an absolutely fine reason. I just don't use it because it's not perfect. And once we have a ratio that is set up with what we want, we can now start to substitute in information that we know. Right, so the first thing is, if you remember, this AD and DC, we have a ratio for that. So we can actually substitute that in immediately. So we know that, I'll move it up now. EB over AE has the same ratio as DC over AD, which is 4 over 5. And this is all from that pink information that we wrote down earlier from the given fraction we had. So now that I know that, I can also start to fill in other bits of information that I have. I know what the length of AE is. So if you have a look over here, AE is the side length in orange there. So that would be 3x minus 5 plus the 2x. That's the length of AE. Yes, it's in terms of x, but that's fine. We can deal with that in a second if we need to. Oh, technology is really testing all of my patience today. But we know that EB over whatever AE was, which was that 3x minus 5, to 4 over 5. Okay, so we're starting to get somewhere. We're starting to solve for EB. Hopefully some of you can already see what the issue is, but we'll get there in a second. We can simplify that denominator. So this would be EB is over 5x minus 5. And if you want to go a step further to solve for EB, which you're welcome to, EB is equal to 4 times all over 5. So all I'm doing here is I'm multiplying the left and the right by my denominator. So I say 5x minus 5. So I could get rid of the denominator, but obviously then you also have to multiply it on the right side. Okay, so that's what we got an EB as. Now the question said determine the length of EB. It didn't say anything about in terms of x. So now that we're at this point, what we need to realize is that we need to know x's value. Now go back to what I've given you. We've already used the big triangle ABC. So we've already gone and worked with a ratio in ABC. We have not yet used the triangle that contains the green parallel line. So that would be triangle. That would be triangle AEC. So there's like slanted looking triangle over there. Now, if you have a look, AF in that green triangle corresponds with AD, and FE in that green triangle corresponds with DC. AE or AF and FE are all in terms of x, and we know what the ratio of AD to DC is. And what that allows me to do is it allows me to go and solve for x. So in that triangle, I'm even going to put a little note here that I'm working in triangle ABC. You can obviously write that if you want to, you don't have to. What we have established is that the ratio of AF over FE is equal to, and again match it up, AD over DC. And this is all still because of my prop theorem, but now I'm working with parallel lines FD and EC. Okay. Yeah. And now once again, much like I did before, I'm going to start to fill in the information. So AF was 3x minus 5. FE was 2x. And remember, AD, if you look back in the pink, was at 5 over 4. AD over DC. And now this is an equation that I can go and solve. So if I go and solve my equation for x, remember I'm going to cross multiply here. So this would be 4 times 3x minus 5 is equal to 5 times 2x. If I distribute, this would be 12x minus 20 is equal to 10x. Inverse operations, 2x equals 20. And so once I solve for x, I get that x is equal to 10. Now that I know what x is, remember we've got an expression for EB in terms of x. So now all I need to do is I need to go and substitute in. So therefore, we know that EB is equal to 4 equal to 4 times 5x, which we now know is 10, minus 5, all over 5, and then you just chuck that into your calculator. You don't even need to try and work it out in your head. And so therefore, EB is equal to 36 units. Okay, so guys, really, really important for these types of questions, because hopefully what you see is that there's just so much information going on. If you have a look, or if you consider what was given to us, we were given a triangle, but essentially we had two triangles in there. So we had not only triangle ABC, but we also had triangle AED. Then we had a whole bunch of parallel lines that we needed to work with. And so what I find easiest is to start by setting up the ratio with the side length or the side segment that you want. And that's exactly what I did as my first step. I said, okay, I know I need EB. So let's start by setting up a ratio. Again, there's lots of different ways you could set up the ratio, but think about the information you have. I could have said EB over AB, absolutely. But the problem is, I don't know what EB is. So there's no way for me to find an expression for that whole side length AB if I don't know the bottom segment. And so what that means is I have to look very carefully at the fact that I knew that AF was 3x minus 5 and that FE was 2x. And from there, I could then go start setting up my ratios. Now, this method, what will often happen is you will see that there's information that you are missing. So once we had what we saw was that we were missing the value of x. That's fine. Once you have missing information, you just go and find it. We could go and find the missing information of x because we saw in that green triangle, I not only had the ratio of AB to DC, but I also knew that AF and FE were 3x minus 5 and 2x respectively. And so then I could easily set up an equation and solve for x. And once I had x, all I needed to do was substitute back into my expression. Now, obviously, guys, it seems a lot easier when you do it together, when you do it with me, when someone else explains it to you. But this is what I found is the easiest approach. And I'm not necessarily saying it's the only approach. Some people like to immediately solve for x and then go from there. That's absolutely fine. There's nothing wrong with that. We're obviously going to have to find x at some point, whether you do it as your starting point or your end point. Really makes no difference. But I like to set up my ratio so that I know exactly what I know and exactly what I still need to find out. And then I can go back to my diagram and say, okay, I know I need to work out x or work out the length of DC or whatever the case is. And it just gives me more focus in terms of what my next step needs to be if I know what information I'm missing. All right, so let's take a screenshot. Obviously, guys, please ask me questions as we go along. I know that there's a lot of information, and again, it's not necessarily everyone's favorite section, but please do ask me questions as we go along. Okay. Right, and obviously, if you don't feel comfortable raising your hand or unmuting yourself, you're welcome to just send a message directly to me or on the chat, whatever you're more comfortable with, but please do ask. Right, so let's have a look at example 2. Similar sort of situation, we have to read our information carefully here because not everything is on the diagram. We have been told in triangle QRS, so that's the big main triangle for lack of a better description, T and U are points on RS, and W is a point on QS, such that QT is parallel to WU, and QR parallel to WT. So this is what I say, not all your information is there. So QT parallel to WU. These are the green lines here. I'll put little parallel line arrows on them as well. That's obviously important to know. This just going to fight with me, so you know, whatever. Right, so remember guys, I know this seems like a silly statement. Parallel lines have the arrows. Equal line segments have the strike or the line marks on them. Right, so we're given that, and QR parallel to WT. These are now my pink parallel lines here. Oy, oy, oy. Again, I'll put parallel line markings on them just in case that's easier. Some very dodgy looking arrows, but we're just gonna roll. Okay, so we've been given parallel lines. Now because they've given you this information, you can use it. So if QW is equal to 12 millimeters, so I'm going to fill that in for myself. QW is 12 millimeters. WS is 11 millimeters. TU, so this whole segment over here, is 6 millimeters. Find the length of RS. Now be mindful of where RS is. RS is this entire side in my big triangle. That's what I'm wanting to find. So again, we're going to have to figure out what do we need in order to get this answer. Now, the first thing I just want to point out, which might seem really obvious, is because you've got WQ and WS, you do actually know the side length or the length of SQ. 11 plus 12 is 23. So this is 23 millimeters. Just something to bear in mind. So always look at what you have and what might help you find. So we know we want RS. So that's what I'm going to start with. I know I want RS, and I'm now going to start setting up a ratio. Now, if you consider which triangle RS is in, and when I say which triangle, remember we've got the pink triangle. Let's do this, which is QS. Okay, we're just going to roll through it. QSR. And we've got the green triangle, which is QST. Now, the reason that's important is because we must be mindful of what side lengths actually exist in my triangles. SR, so the side length I'm wanting to find, only exists in the big triangle QSR. So when I look for my ratio, I must bear that in mind. So SR, now I have to decide what it's going to be over. Well, I don't really have much. That's okay. That's not great, but it's okay. I'm going to go over ST. It's fighting me. I'm really over it. ST. Now the reason I'm going to go over ST, and ST is the side length over here, is because I already know that UT is 6 millimeters. And I can see that in my green triangle, I could set up a ratio for SU over UT, and I could get the whole side length ST. So I can get there. Granted, I don't know that information now, but I can get there. So I'm going to go RS over ST is equal to, now in my pink triangle, I need to match up what those sides that I'm working with. RS, the whole side length, matches up with the whole side length QS. And ST, which is the top segment, remember in the pink triangle, matches up with SW. Remember your reason. And remember your parallel lines, WT parallel to QR. So I'm just going to say this again, because again, I know that this is not the easiest thing in the world to see. ST, so they're in orange, matches up with SQ. ST, now remember we're in the pink triangle, matches up. If you now go straight across, oh gosh, let's draw a better arrow than that. If you now go straight across from ST, matches up with SW. So you remember we have to match up the corresponding sides, otherwise we're going to get absolute nonsense. So that's how I got that ratio. RS over ST is equal to QS over SW. Let's fill in what we know. So let's substitute the values that we know. I don't know ST. Obviously, RS is what I'm looking for, so I obviously don't know that. QS, remember we spoke about the fact that QS is the whole thing, so that's 23 millimeters over SW. 23 over SW, which is the 11 millimeters we were given earlier. Let's just not a second. 23 over 11, right. So that's what we have. Now remember, our goal is to find RS, and as I said to you earlier, if you want to now isolate RS for yourself, that's fine. RS would be equal to 23 over 11 times ST, because you would times the denominator away. And now you know exactly what you need to get. What we can see is that based on what we have calculated, I need to find the value of ST. Now I've just worked in the pink triangle. So these parallel lines that I use WT and QR in order to use the first set of prop theorem, this was in the pink triangle. I haven't yet used the green parallel lines, so I'm going to have to use them at some point. And as I said earlier, this is how we're going to find ST. So ST is in the green triangle, the whole side length. And we've got UT, so I'm going to put that over UT because I have that information. Which means that, and if we match it up, the whole side length is SQ over, and if you match up UT, that's WQ. Prop theorem, WU parallel to QT. Now I'm actually using my green parallel lines. ST is obviously what I want. So ST over UT was 6 millimeters. SQ was that 23 we've already spoken about, and WQ is 12, which means that ST is equal to 23 over 12 times 6. So just through setting up a ratio in terms of what you need in order to get RS, you were able to work out what ST is. So if you just chuck that into a calculator, obviously you don't need to try and do that in your head. That gives you 11.5 units. So that's what ST is. And now that you know what ST is, you can substitute it back into that equation. So now that we know that RS is equal to 23 over 11 times 11,5, because that's what ST was. And so that means that RS is equal to 24,04 units. Oh. So again, grade 12s, yes, if you've got other ways to do this, by all means, you use the method that works best for you, obviously. But just bear in mind that if you can set up a ratio based on what you know you need, so I know I need RS, you can then figure out exactly what it is you don't know, and you can go back and work it out. And that's sort of how I approach these questions. I start with setting up a ratio I know I need. I know I need RS. Let's set up a ratio with that. Then I can start to see, okay, well, I don't know what ST is. Maybe I don't know what SW was. I don't know. A whole bunch of things I don't know. And then I can use the information that has been given to me to go and work it out. Now, more often than not, what's going to happen, and this is why I've sort of been saying it over and over, is that to set up your first ratio with the side you want, you're going to use one set of parallel lines. In order then to figure out your missing information, you're going to use the other set of parallel lines. So we started by using the pink set of parallel lines just to get an expression for RS. But then we used our green parallel lines to go a step further and work out the information that I didn't know in terms of ST. So that's often going to happen, and that's one pair of parallel lines will get you the ratio with the value you want. The other pair will help you get the information of what's missing in order for you to find what you want. Again, if you've got your own method that works for you, absolutely. This is just what I have found works best for me, and is the simplest way to do it. Again, if you had seen that you would need ST and you had gone and worked out ST first before you set up your ratio, fine. There's nothing wrong with that. Personally, I would not have been able to look at that under like exam pressure or test pressure and look at that diagram and say, okay, I know at some point I'm going to need ST. Let me just go work it out. That's not something that my brain in a panicked or anxious state would know how to do. And so that's why setting up that initial ratio first guides you to say, okay, this is, you know, our S's, the 23 over 11 times ST. You don't know ST, go and work it out. Okay, so let's take a screenshot. Again, if you've got questions, please ask. Alrighty. Let's have a look at example 3. Okay, so example 3 is bringing back in the idea of similarity. So we've done 2 proportion examples, then we're going to have a look at the similarity example. Bringing back in this idea of similarity for us. So if we have a look in the diagram, EF is parallel to CGD. Now don't stress about the fact that there's 3 letters there. It's just because on that line segment, there are 3 points. So if we go and have a look at the bottom, there's CGD. Nothing wrong with having 3 letters to make up a line segment. It's not usual, but obviously it's absolutely fine. There's just 3 points along there. It's parallel to EF and BEC, so exactly the same thing. Nothing wrong with that. Is parallel to FG. BEC is down the left-hand side here. FG sort of cutting the triangle in, let's not say in half because we don't know it's in half, but cutting the triangle. We want to prove that triangle BF is similar to FGD, remember? Spoke about how important it is that the letters are in order. Most of the time, if not all of the time, we always give them to you in order. It's very rare that we give them to you in the wrong order, but we always just double check at the end, and then we want to prove a ratio. We're not going to stress about the ratio right now. We're first going to prove similarity. Okay, what I'm going to ask you guys to do is try question A by yourself, because this is what we were doing on Wednesday last week. So this should still be somewhat fresh in your brains. I want you to try and prove that triangle BEF. So triangle BEF is this green triangle up at the top here. Is similar to triangle FGD, which I'll do in blue, which is this triangle sort of at the front of the bigger triangle. I don't know how to describe it. Okay, so I want you to prove they're similar. Give it a try, see what you get, and then we'll go through it and give you 3 minutes, and then we'll go through it. Okay, let's have a look. If you're not finished, don't stress. Just have a catch up as we go along. Now, guys, remember, for similarity in triangles, there's only two ways to prove it. Either we show that the sides are in proportion, or we show that all three corresponding angles are the same. Now, remember, we can't use sides in proportion if we don't know anything about the sides. It's just impossible to do. So based on the fact that I know nothing about any of the sides in any of those triangles, I'm going to have to use angle, angle, angle. So we state what triangles we're working in, BEF and FGD. And I know I have to make 3 statements. We're looking for angles that are the same. Now bear in mind we've got some parallel lines here. So based on the orange parallel lines, I can see that angle B is a corresponding angle with angle F. So it's that F shape that we learn about in like grade 8 and grade 9. So angle B is equal to F3, corresponding angles. And just remember, anytime we use corresponding co-interior or alternate angles, you have to state the parallel line. So in this case, BC parallel to FG. That's my first angle pair that I've got. Right, if you now go and have a look at the pink parallel lines, F1, wait, trying not to lose my cool with technology, but it's very hard. F1, which is this angle over here, corresponds to angle D. So again, we've got corresponding angles because of the other parallel lines we have, EF and CGD. So F1 is equal to angle D. You can say BDC or CDB if you want, but there's only one angle D. Again, this is because of corresponding angles. But now we're using the pink parallel lines, EF parallel to CD. And remember, we spoke about this on Wednesday. The second you've got two of your three angles equal, it has to mean the third is equal. So E1 is equal to G2 because of sum of angles in triangle. Now that we've done that, we can say, therefore, triangle BEF. Now make sure these match up when you say that they're similar. So angle B matches up with angle F. So F. Angle E matches up with angle G. G. And angle F matched up with D. FGD. Angle, angle, angle. So we have proven that those triangles are similar to each other. Remember, the second you've proven that they're similar, you know that all sides are in proportion, or all corresponding sides are in proportion. And we know from Wednesday's lesson that this is going to help us answer question B. So when we get to something like question B, remember what we now want to do is we want to set up the corresponding sides in terms of fractions. It wasn't very well described, but hopefully you know what I mean. If not, this is what I mean. So BE corresponds to FG. So we set up our ratio. BE corresponds to FG, which is equal to, now we move to the next two letters, EF, which corresponds to GD. And then we move on to the first and the third pair of letters, which in the case of our triangles that we have here is BF corresponds to FD. And this is all true. We can say all of these ratios exist and are true because of corresponding sides in proportion. Because we have proven the triangles are similar. Now that we've done that, we can go back to our ratio that we're looking for. So if we go and consider this, we want DG over FG is equal to EF over BE. Go to your ratio that you just set up and find which ratios or which fractions contain those letters. So there's DG, there's FG, here's EF, here's BE. So I actually want to work with the first two ratios here in order to prove the statement is true. So if I write those down, BE over FG, obviously you don't have to rewrite them if you don't want to, is equal to EF over, and I'm just going to swap the D and the G in around, just put it in alphabetical order, it really doesn't matter though. Okay, now we have to make it look like the ratio we want. So if you look at this ratio, we've got DG over FG. So basically what that means, I want to bring this DG, and I want to bring it up, and then on the other side, I've got EF over BE. So I want to take this BE and bring it down. There's nothing wrong with doing that. Because you're swapping them, essentially you're doing a whole bunch of inverse operations, which I'm happy to show you. But there's nothing wrong with you just going straight away and swapping. However, if you don't really believe that you can swap it, here's how. The first thing I would do is I would times both sides by DG to get rid of it in the fraction. So this would be BE times DG over FG is equal to EF. Now I want to bring the BE down, so I would now divide both sides by BE, which means I've got DG over FG is equal to EF over BE. And that's exactly what I wanted to prove according to the question. So again, you could just swap them. There's nothing wrong with that. It's absolutely fine. But if you wanted to see the mathematics of why you can just swap them, there it is. Basically just, as I've said many, many times before, manipulation. Alrighty, so what we have here is a similarity question, very similar to what we had on Wednesday. Using similarity, going to prove a whole bunch of different things. In this case, the ratio one being most important. So let's take a screenshot. And then we'll have a look at how we can now incorporate this idea with our circles. Because remember, like I say, circles are the bulk, we'll then bring in these questions within the circle geometry.
Sorry, can you please explain how you switched DE and DG? I don't understand how it went from the denominator to
Sorry,
the
can I
numerator.
please?
Sorry?
Can you repeat your question for me? I didn't hear the end bit.
Oh, could you please explain how you put DG at the with the numerator with DE, like how you switch those around? I don't really understand that part.
Okay, cool. So let's just rewrite this over here. So BE over FG is equal to EF over DG. So that was what we initially have, and we now need to do the swap. So our end goal here is to have DG over FG is equal to EF over DE. So this is my end goal. But like you say, how do I get there? So now it's all about manipulation. Like I say, what I can see is that I have to somehow get DG to this numerator. And in the same vein, I also somehow need to get EF, no, not EF, nonsense, BE to the position of DG. So this is where manipulation comes in. I know that I have to get DG to my numerator, which means I need to times it out of the denominator on the right-hand side. But remember, in an equation, what you do on one side, you do on the other side. So I'm going to times by DG on the left. That therefore leaves me with, on the left-hand side, DG times BE, which is still my numerator, over I'm trying real hard not to lose my cool here. It's making it tasty, so let's just go here. DG times BE in the numerator, still over FG. But now because I've timed the DG away on the right-hand side, I just have EF on the right. Now what I want to do is I need to bring this BE and I need to bring it down. Now the only way for me to introduce something that's in the numerator into my denominator is to divide by BE. So if I divide by BE, BE divided by BE is gone. But I now need to divide on the right-hand side by BE. So in dividing by BE, I end up with DG left in my numerator over FG, which is still there. equal to EF over BE. And now I've got what my end goal was. So it's all just manipulation. When you want to bring something from your denominator into a numerator, you would multiply. That's the only way we can get it into the numerator. If we want to bring something from our numerator into the denominator, we'd have to divide. It's the only way we can do that. You don't need to show the multiplication and division. Obviously, you're welcome to if you want to. You're welcome to just swap it and go. But this is the inverse or the mathematical method behind it. Does that make a bit more sense? I hope so. Just let me know if not.
It really does help. Thank you.
Say again?
I'm saying it really does help. Thank you.
Okay, cool. All right, guys. So let's have a look at example 4 here. So don't be scared. I know circles scare us, and especially when we chuck 2 circles in there. But let's just read it carefully, see what we have going on here. So we've been told that circle ABC, now guys, when we say circle ABC, we're saying that the circle passes through those points. So ABC passes through the points on its circumference A, B, and C, as well as ABD. So again, it's passing through the points A, B, and D, intersected A and B respectively. AC is a tangent to circle ABD, so tangent to the smaller circle on the right, and AD is a tangent to circle ABC, the slightly bigger circle on the left. Prove that. I'm not even going to stress about proving anything just yet. Let's just understand what we have going on. So, tangents are very important because the second I mention tangent to you, especially in a circle, you should automatically be thinking, cool, tan chord theorem, tan perp rad, all of those fun things. Now, because we don't have any centers here, we obviously can't use tan perp rad, but maybe tan chord theorem will work. So let's just establish what's going on here. Circle ABC is this big circle over here in yellow. You know, we'll make it work. All right, in yellow, there it is. And we were told that AD is a tangent to that circle. So here's AD being a tangent to that circle. I'll remove the highlighting in a second. So that's the first bit of information that we have. And remember, we need to be thinking tan chord. If we just think about tan chord already, AD is my tangent. I can see that there's an angle created A2 between the tangent and the chord, which means that would be equal to angle C. Just start thinking about these things. The next bit of information we were given is the fact that circle ABD, which is the slightly smaller circle. Oh, come on. No one's fighting. Slightly smaller circle here in pink, whatever, has a tangent of AC. So AC is this pink line over here. We can clearly see that's a tangent. Again, think about your tan chord theorem, A1 and angle D. Now, the reason these are all important to think about is because if you go and have a look at your question, I'm asking you to prove that a ratio is equal, essentially BC over AC is equal to AB over AD. And I'm asking you to prove something squared is equal to the product of something else. We'll get there. But those ratios automatically should be making me think of similarity. I can only say that these ratios in question A are equal if I know that the triangles that contain these sides are in proportion. If you think back to the question we've just done, the only way I could set up fractions was once I knew that my triangles were similar and everything was in proportion. So this is what I'm going to have to do here. Now, in order to do that, because again, there's a lot going on in this diagram, I now need to somehow figure out what triangles I'm working with. Use your ratio that you've been given. So we've got BC. I'm just going to highlight the sides that I have. BC, AC, AB, the side in the middle, and AD. Automatically, by highlighting those sides for myself, I can very clearly see which triangles I need to prove are similar. I need to prove that triangle ABD, so this triangle here on the right, is similar to this triangle ABC on the left-hand side. Those are the triangles that contain the sides that I want to use in this ratio. Those are the triangles I have to prove are similar. So remember, we always start by stating which triangles we're working with. So in triangle ABC and triangle ABD. Now my order here is definitely not correct, 100%. I will make it correct in a second or two, but let's first prove the similarity. I have to have 3 statements. I know nothing about the side, so it's going to have to be angle, angle, angle. And this is where the tan chord situation comes in. So if we go and have a look, I've already said to you that because of this chord AD, this chord is tangent AD, and the chord A2 is equal to angle C. So that's one thing we can already say. Angle A2 is equal to angle C, and this is because of our tan chord theorem. Because of tangent AC to the smaller circle, and then we have this chord over here, I know that angle A1 is equal to angle D. And again, tan chord theorem. And because I've got 2 of my 3 angles, I can now say that the third angle, which is B1, let's get that with right, B1 and B2 are equal to each other because of sum of angles in triangle. So if we just highlight for ourselves what we have going on here. Oh, column is falling. So we say that A2 is equal to angle C. Technology just hates me today. We're rolling with it. We also made the statement that angle D is equal to angle A1. Those are both the tan chord theorems that we used. And then finally, we said that B1 and B2 are equal to each other. So we can see our corresponding angles there. And because I've proven similarity, I can now go and do the rest. Now I can say, therefore, triangle ABC, now make sure it matches up. So ABC is a triangle on the left. Angle A1 matches up with D, so similar to triangle D. Angle B, so the pink, matches up with B. And angle C, the yellow, matches up with A2, so A. Angle, angle, angle. And because I have this information now, I can potentially use it to go and show them. Okay, so guys, just in terms of a question like this, what you need to be mindful of is the fact that, I'm very disheveled here, is the fact that sometimes I don't ask you to prove similarity and you have to know to prove similarity. You knew to prove similarity in this case because I was asking you to show that ratios were equal. The only way you can do that is to know that the sides are in proportion. The only way to know the sides are in proportion is to prove similarity. So sometimes you do have to go that step further and think, okay, well, the only way for me to do this is to do that. And you have to do a bit of work before you can get to your answer. All right, so I want you to take a screenshot of this. I want you to try these 2 questions. I've done most of the legwork for you. You now just have to go and figure out that ratio and manipulate where you can and try and have a look at B. What we'll do is we'll go through this first thing on Wednesday. So just remind me in case I forget, but we will go through this first thing on Wednesday.